Okay, welcome to Chapter 8. This is our Unit 5, and in this chapter we're going to be looking at chemical formulas and how we use those chemical formulas, the reactions that are occurring. So the first thing we need to know is what a chemical reaction is and see evidence for a chemical reaction. Well, for evidence of a chemical reaction, often we're going to have one of four things. So this is evolution of heat and light. So in this one we have the decomposition in the little example here of ammonium dichromate proceeds rapidly, releasing energy in the form of heat and light. Well, that is evidence of a chemical reaction if we see the release of heat and light. However, it also could be evidence of a chemical reaction if something is very cold, like a cold pack. There is a chemical reaction going on, and the feeling of cold there is evidence of a chemical reaction. So for this one, I like to say change in temperature, kind of as a more general way to describe indication of a chemical reaction. Number one, we could have a change in temperature. What else could we have? Well, notice on this page, let me clear it off so we can see, we have two example reactions. Here we have just baking soda added to vinegar, or what we call acetic acid, baking soda being sodium bicarbonate. So we have sodium bicarbonate, NaHCO3, being added to acetic acid, HC2H3O2. So that's our chemical reaction. Notice, or that's our reactants anyway. Notice we're seeing bubbling. That's evidence of a chemical reaction. And sometimes we have to be careful that bubbling is the production of a gas. Another way we can witness a gas being produced is if there's a smell. That could be a gas coming off. So we have to look for a smell coming off, a different smell, bubbles. That's the production of a gas. So change in temperature, production of a gas. Production of a precipitate is one we don't think of often, but sometimes when we mix two liquids, they'll form a solid. So this yellow substance coming out is actually a solid. It's called a precipitate. So if we mix two liquids, get a solid, that's a precipitate. That is evidence of chemical reaction. So a change in temperature, production of a gas, production of a precipitate, or a color change indicates evidence of a chemical reaction. Very briefly there. So now we need to look at our actual chemical formulas. When we look at our chemical reaction, there's some symbols we should be aware of. Now we know there's going to be elements on either side. So one thing I want to add maybe to this list is we know that we have reactants are on the left side of the reaction, and then when we have the arrow, we have products on the right side of the reaction. Well, there's a lot of things we could have around them or alongside that arrow that we want to look at here, that some of them we'll have seen before and some of them we won't. That arrow itself means yields, and it points in the direction the reaction is going. It is also possible to have a double arrow, meaning the reaction could go in either direction. It's what we call an equilibrium reaction. Now, the other things you'll see on this chart are state symbols that we've already used a little bit and looked at. S meaning solid, liquid being an L, gas being a G, AQ meaning the reaction is dissolved in water. And a lot of our chemical reactions do happen in water, so it's an important state, not really a state symbol, important, symbol to have and be aware of. We can also see a couple other variables for forming a gas or forming a liquid, or forming a solid, I should say. If we form a precipitate, sometimes you'll see a down arrow if you mix two liquids. Sometimes if a gas is formed, you'll see an up arrow. Those aren't as common as just the state symbols that are there regardless. A couple other things that we might see above the arrow that we should be aware of is if there's a triangle or it says heat, that means the reactants need to be heated for the reaction to go. If we see a certain pressure value or just the word pressure, that means the reaction has to happen at something exceeding normal atmospheric pressure. In this case, it says 2 atms. That means 2 atmospheric pressures. That means twice the normal pressure of the atmosphere. Again, that would be like at sea level, like normal atmospheric pressure. A couple other things. It could happen at a certain temperature. So instead of just heat, it could say it happens at a certain temperature. And this one is carried out at a colder than normal temperature, 0 degrees Celsius, freezing. And last one shows a catalyst. And a catalyst could be a lot of different materials above that chemical symbol, the yield sign. Often it will actually be a transition metal like platinum or palladium. In this case, it's magnesium dioxide. What a catalyst is, by the way, is something that's going to increase the rate of reaction, but it's not going to affect the yield of the reaction, and it's not going to actually change the reaction itself, or react itself, I should say. Well, what do these reactions mean, and how do we write them? Well, let's look at this reaction as our first example. So we have hydrogen, and really if we wanted to write it as a complete chemical formula, we'd put its state as gas right next to hydrogen, a G right next to chlorine there, and probably a G over here next to our hydrochloric acid, which also is a gas at room temperature. Now, if we look at these, and I'm going to erase that just to make everything a little bit clearer here as we begin, they've written this out. Now, how do they know it's H2 and Cl2? Well, those are what we call diatomic elements. They are elements that can bond to themselves and actually do because they are so reactive. The way we know what a diatomic element is we have a little saying called heck no halogens. So what that is saying is that hydrogen, nitrogen, oxygen, and all of our halogens at standard temperatures, standard pressures and temperatures exist as diatomic elements. So we have H2, N2, O2, then we'd have F2, Cl2, Br2, and I2. So anytime we're using any of those elements, we assume at normal conditions they are diatomic. So in this case, if they said hydrogen reacts with chlorine, you'd know it's H2 plus Cl2. Now on the other side, H2 plus Cl2 reacts to make hydrochloric acid. Now one thing we want to look at is notice they have a 2 here in front of the hydrochloric acid. Now why do they have a 2? They need to have a 2 so that we have the same numbers of elements on both sides of the chemical reaction. So H2, there's actually 2 hydrogen atoms. Cl2, there's 2 chlorine atoms. If those things are going to react, one of these hydrogens can attach to each of the chlorine. So on this side, we can't just write HCl because that would just be one of these. And just one of those can't exist. We can't just get one of those out of a reaction. We need to obey conservation of mass. And we can't create or destroy any of these atoms. So if we have 2 hydrogen atoms and 2 chlorine atoms here, we need to have 2 here after the reaction. So that is what the balance equation is telling us. There we have 2 hydrogens here, we have 2 chlorines on this side of the reaction. Over here, now we have 2 hydrogens and we have 2 chlorines. So it is a balanced chemical reaction. Now let's look at what else our chemical reaction says. In this case, the 1 is saying we have 1 molecule of hydrogen, 1 molecule of chlorine, and 2 molecules of hydrochloric acid. And again, we need those 2, so it's a balanced reaction. We could also up these into moles, and that's normally what we'll do. And we'll say we have 1 mole of hydrogen reacting with 1 mole of chlorine to make 2 moles of hydrochloric acid. That's perfect. That's exactly what the reaction says. That's exactly what we need. Notice another interesting thing. If we look in the periodic table, and we find the mass of 1 mole of hydrogen, we'll find is 2.02 grams. So each hydrogen is 1.01 gram per mole. And if it's H2, we'd multiply it by 2. That's where we get this 2.02. Notice if we do the same thing for chlorine, each chlorine atom is 35.45 grams per mole. There's 2 of them here, so the molar mass of our diatomic chlorine is 70. Now notice this on the other side. The mass of an individual chlorine hydrochloric acid molecule is 1.01 plus 35.45. So the mass of 1 is 36.46 grams per mole. That would be for just hydrochloric acid. But notice we have 2 hydrochloric acids because, again, we had diatomic elements on this side. So notice they take 2 times that mass, times this mass that we add up, and notice the mass 72.92. Well, if we go back and we add this mass to this, we will find that the masses are equal. We have conservation of mass. And we're going to do reactions like that over and over again, that if we know how much reactants we have, then we know the mass of products that we should create. Let's look at another reaction. Here we have methane, and methane is burning. Methane is natural gas, and it burns in the presence of oxygen. Again, oxygen is a diatomic element, heck no halogens. When any carbon compound burns, we get 2 products. We get CO2 and water. So let's look at what they have written here. Notice CH4 needs 2 moles of oxygen, of diatomic oxygen, to react with it, to make CO2, and then it will make 2 water. Now let's look at why they have those balance coefficients in front. Well, if we add up what's underneath here, notice we have 1 carbon, we have 4 hydrogens. This indicates we have 4 oxygens. On this side, there's 1 carbon, and there's 2 oxygens in this structure. If we have a 2 in front of our water, we have 4 hydrogens and 2 oxygens in this structure. So we have a total of 4 oxygens here. We have 2 plus 2, we have 4 oxygens on that side. If we look at our carbon, 1 carbon here, 1 carbon here. Look at our hydrogens, 4 hydrogens here. Now we have 4 here. That is what we want to make sure that we have whenever we balance our chemical reactions. So here are some examples from your book, and I'm going to start with this one. Aluminum reacts with oxygen to produce aluminum oxide. And so I want to take that word formula, and you'll be doing this quite a bit, and I want to change it into a balanced chemical formula. So this is a word equation. I want a chemical equation. So aluminum, Al, is aluminum, reacts with oxygen. So I'd say plus oxygen. And oxygen, again, we have to remember is diatomic. It is O2. The other thing I'm going to throw in is I'm going to throw in my state symbols. Aluminum, I know, is a metal. If I look on the periodic table, it's going to be a solid. Oxygen is going to be a gas. On the other side of this reaction, produce means put down your yield sign. It produces aluminum oxide. And now here's what you might be asking. Well, what's aluminum oxide? Well, that's what we should have learned in the last chapter, is how to put together these formulas. So aluminum is Al. Looking at its place on the periodic table is +3. Oxygen is O, probably -2. So if I cross those charges, I get Al2O3. And that doesn't say it, but should be a solid. So we produce aluminum oxide. So we have a chemical equation, but it's not balanced. The next thing we want to do is go through and balance this. So let's just count up what we have on our reactant side of the equation. So these are our reactants. I have 1 aluminum, and I have 2 oxygens. On my product side, I have 2 aluminums, and I have 3 oxygens. Now, there's no hard, fast rules about how to balance equations, but typically, we're going to balance metals first, leave the oxygen, the hydrogen for later. So I have 2 aluminums. I only have 1 here. Well, I can't put a 2 here. That would change the formula and how aluminum bonds to itself. That would be weird. I can only put coefficients in front, large number coefficients in front. So we're not changing subscripts or superscripts. We're only putting values in front. So I'm going to put a 2 in front of the aluminum. That's going to give me 2 aluminums. And I can do that because that's showing everybody the ratio that this thing is actually going to react in. Just because we write aluminum and oxygen, that's not telling us how the reaction is going to occur, how much of each it needs. We have to balance the equation to figure that out. So I have 2 aluminum. That's not working. Now I have to check these 3 oxygens, or 2 oxygens, I'm sorry, here and 3 over here. Well, I could, not really a good way to do this. We want to work in whole numbers, right? So I could put a 2 there. That's not going to work. You know what? I think I'm going to need a common denominator. So I'm going to have to put a 3 here. That will give me 6 oxygens. And that'll only work if I put a 2 over here. If I put a 2 there, that will give me 6 oxygens. Now my oxygens are balanced. But what happened in the meantime is I changed my numbers of aluminum. Now I have 2 in front and a 2 subscript. That's giving me 4 aluminums. So I'm going to have to go back to that side. I'm going to erase this. And you can erase all you want when we're balancing equations. I'm going to have to put a 4 there. Now I've written a balanced chemical equation for the word formula that they gave me. 4 aluminums plus 3 oxygens are giving me 2 aluminum oxides. I have the same number of elements on each side, which also means I'm going to have the same mass in my reactants as in my products. And what I'm going to be able to do is if I know my amount of aluminum, I'm going to predict the amount of oxygen that's going to react with it and the amount of aluminum oxide we'll produce. Because again, what this is telling us is 4 moles of aluminum will react with 3 moles of oxygen gas to make 2 moles of aluminum oxide. And we want to remember over and over that that is what a balanced equation is telling us. It's telling us the amounts. We could change those amounts each to grams if we wanted, because we can look up their masses on the periodic table, and then we can find out how much we're going to make in each step. Okay, the next one I want to look at is the C, iron 3 oxide. So we have iron with a +3, oxide, ID ending means it's just oxygen, has -2, so iron 3 oxide would be Fe2O3. Most of our ionic compounds are solids, so we should know that most of our ionic compounds are going to be solids. They're solids at room temperature. Reacts with carbon monoxide. So now we have a covalently bonded compound that's reacting with carbon monoxide, carbon with 1 oxygen, which is gas. To produce means put in a yield arrow. So this is supposed to be an arrow, by the way. Maybe I'll color it in. To produce iron, so just pure iron. Iron as a solid, it's a metal, should be solid. And carbon dioxide as, again, carbon dioxide is a covalently bonded compound, one we've heard of before, a gas. Now, we've written out our formula. We have our state symbols. Now we need a balance. So what we're going to do is just do an accounting of what we have on each side. On my reactant side, I have 2 irons. I have 3 plus 1. I have 4 oxygens to start with, and I have 1 carbon. On my product side, I have 1 iron, so that's the first thing I might want to work on. 1 carbon, and 2 oxygens. So notice I have a problem with my oxygens. I have problems with my iron. I have problems going into this problem. So maybe I'll start with my iron. So there's 2 here. There's 1 here. Put a 2. That's a little bit too easy. I might run into a problem I see here quick. Carbons are okay for the moment, but now look at our oxygens. We have 4 here and only 2 here. So I may want to start by putting a 2 on this side. That would give me 4 oxygens, so they're balanced, but notice that also changes my carbon number, which is just fine. Let's go to the other side and change our carbon number. So changing my carbon number there, no problem. I'm going to go to the other side now, and I'm going to change my carbon number. I'm going to put a 2 there. So now I have 2 carbons on this side. But wait, what happened? If I put a 2 there, now I actually have 3 oxygens still here, but now I have 2 oxygens. I've changed my oxygen number 2. I have 5. Ooh, that also is not going to work for me. We have to find something else. Notice, okay, so let's go back and try something different. Instead of putting a 2 there for the carbon, I don't really need to put a 2. See, because I don't want to increase the value of this, because I already have my irons balanced, and if I increase, then I'll just make more oxygens. I think I'll run into trouble if I go in that direction. So I'm going to erase this. I'm going to say, well, you know what? My experiment with my carbons and my oxygens didn't work. I'm going to go back to where we started. And this happens all the time when you're balancing equations. So go back. Let's see. We actually had 4 oxygens. We had 1 carbon. We had 1 carbon and 2 oxygens over here. There has to be something else to make this work. Well, I tried 2 carbons, and that didn't really work. You know what actually might be the problem is I have a 3 and 1 oxygen over here, so I have this odd, this is an odd number, this is an odd number, this is an even number. Now notice they're making 4 right now, but I'm going to run into a problem trying to make those always come out. So here's what I'm going to do. I'm going to put a 3 here. So that's going to give me 3 carbons. I notice 1, 2, 3, and 3. It's going to give me 6 oxygens. Now I have an even number there, and I have 3 and 3 oxygens for 6. This, I think I can do it. If I put a 3 here, now that gave me 3 carbons, and 3 times 2, I have 6 oxygens as well. So I've gone through and I've actually found a way to balance that. So let's take a look now at the section review that you have. So we should know the difference between our word equations, our formula equations, and our full balanced chemical equations. And we should be able to do things like this. So number 2, let's just try this one. Write a word and formula equation for the reaction in which aqueous solutions of sulfuric acid and sodium hydroxide react to form aqueous sodium sulfite and water. Now, wow, if we didn't know our naming, we should really know it by now. Sulfuric acid and ic acid, so that you know ic acids are always derived from the 8 polyatomic ion. So sulfuric is from sulfate. Sulfate is SO4 negative 2. If it's an acid, that means only hydrogens are bonded to it. That is the definition of our acid. So if it has a negative 2, that means it can bond to 2 hydrogens. So I've got sulfuric acid. Again, our acids are always aqueous because they're always dissolved in water. Sodium and hydroxide. Sodium is Na. It has a positive 1 charge. Hydroxide is OH. It has a negative 1 charge. Knowing our polyatomic ions is just crucial for our going on. If they weren't crucial before, they're crucial now. Oh, time to go. But not for you. They react to form aqueous sodium sulfite and water. So they react to form sodium sulfite. So I have to put sodium together with sulfate. So sulfate's still negative 2. Na negative 2. So that would be Na2SO4. Okay. 2SO4, and water, which is H2O. And water is a liquid. And my sodium sulfate is probably going to be aqueous still. It's probably a salt. We'll learn about whether our salts are aqueous or solids in the future. Now we want to balance it, though. So let me rewrite it quick and look what we have. So we want to be able to balance this reaction. So again, let's take accounting of things. We have 1 sodium here. We have 2 over here. So that might be one of the first things I look at. Notice we have 1. Well, you know what? Here's where I'm going to tell you to be a little bit careful. If you have a polyatomic ion like this, like sulfate, and you see it on both sides, instead of trying to balance those separately, I'm going to just balance that as 1 sulfate. Right now, there's 1 sulfate on each side. So I'm going to balance that as a polyatomic ion. I'm not going to try to split that apart into sulfurs and oxygens. That's a little trick we can do. However, I'm going to have to look at the rest of the stuff. So we have oxide, but notice it's in water. It's not clearly as an oxide on the other side, so I'm going to have to write 1 oxygen just from here. Again, the oxygens in the sulfate are already taken care of, so the mass of them are already taken care of. And then 1 plus these 2, 3 hydrogens. On this side, okay, so how many oxygens do I have that aren't in that sulfate? Well, just 1 oxygen. Okay, that makes it easy. Hydrogens, 2 hydrogens. Okay, so we have a little something to work with. I'm going to start by balancing that sodium. Notice my sulfate is 1 sulfate, 1 sulfate. That's the biggest, ugliest piece of this reaction, so I want to leave that alone. I'm going to put a 2 in front over here. So that 2 is in front of this piece. That means now there's 2 sodiums. I've increased the number of oxygens, so I have 2. And now I have 2 hydrogens plus these 2. That's a total of 4 hydrogens. Let's go to the other side and see if we can't get that. Notice sodium's taken care of. Sulfate is okay. I want to try not to touch that. Now notice I have 2 oxygens, 4 hydrogens, 1 oxygen, 2 hydrogens. I can solve that easy. Put a 2 in front, 4 hydrogens, 2 oxygens. This really just is a process of trial and error. We have to know how to write our compounds, but once we do, when we put different ratios in front, try to get up to the right number so they're balanced on each side. And we might go back and forth quite a bit, and that's okay. Let's do maybe just one more together here. This one here where we have hexane, C6, H14, and it says write out the following reactions. Plus oxygen. Oxygen, remember, diatomic. Heck no halogens. Oxygen is one of our diatomic elements. We have carbon dioxide, which is a covalently bonded compound, and water, or dihydrogen monoxide if you'd rather. Hydroxylic acid if you're talking about it as an acid. So what do we have? Let's take accounting. I have 6 carbons. Over here I have 1 carbon. I have 14 hydrogens. Over here I have 2 hydrogens. Also I have 2 oxygens. Over here I have 3 oxygens. So I don't have the same number of oxygens. I'm going to take care of my carbons first. Leave hydrogens and oxygens for later. So I have 6. I'm going to need 6 of these minimum. That gives me 6 carbons. Changes my total oxygen number. 6 times 2 is 12 plus 1. 13 oxygens right now, which is kind of awkward, but we'll take care of it. Let's take care of our hydrogens now. We have 14. I need 14 over here. Easiest thing would be to put a 7. We will try that. That'll give us 14 hydrogens. What kind of goofy oxygen number do I have now, though? 6 times 2 is 12. Plus there's a 7 in front here. 12 and 7 gives me 19 oxygens. Now, if I could put something in front of that to make this 19, that would be great, but I can't. So here's another little trick I'm going to do. If they come out like this and I need some odd number of oxygens over here, I'm going to just go back and double everything. Because I have coefficients in front of all of these. If I go back and change, I'm going to have to change those coefficients. So I'm going to put a 2 in front here. That's going to give me 12 carbons. I'm going to change this to 12. So I have 12 carbons. And I'm going to change this to 14 so that I have, 28 hydrogens. Because this should now be 28 as well. I doubled it. So they're crazy numbers, but my carbons are balanced. My hydrogens are balanced. Now I just have to look at my oxygens. Now I have 14. Notice now I have an even number here. So now my oxygens are 14 plus 24, because there's 12 times 2. So there's 24 plus these 14. 24 plus 14, 38 oxygens. Now I can do it, right? And guess what number it is? 19. So Now we have a balance equation. Kind of fun to do one like that. Hopefully you get more fun balancing to do in homework.